Okay, I think we're going to get started. So our last two speakers are definitely not least. Each one was brought in for very, very specific reasons, and operating in this same solar system on different planets. So Sharad Goel is maybe quasi-unique, working both in engineering and in computer science and in sociology. So he's able to straddle all those worlds, and he's head of the Computational Social Science Lab. Is that the Policy Lab? And he is not only a voice in academia, but as you can see in his bio, he's been writing for the lay public through the New York Times, the Washington Post, Huffington Post, I think, and a whole variety of outlets about the interface between science and social policy. So here we're going to hear him talk about simple rules for complex decisions. Thanks a lot.
Thanks for the introduction. So I'm going to talk a little bit about how causal inference and prediction come to play together when we're making policy choices. And I'll start with an example which I think is typical of a lot of different policy settings. So this is a pretrial release decision. So shortly after arrest in the US, usually within about 24 to 48 hours after arrest, a judge has to make this high stakes decision of whether or not to release a defendant pending trial or to demand monetary bail. And why is this such a high stakes decision? Well, this is all done under the presumption of innocence, first of all. And even relatively small amounts, what many of us in this room would consider small amounts, $500, $1,000, often individuals who interact with the criminal justice system, they can't afford those amounts of money, and so they're stuck in jail. They might lose their job, they're disconnected from their family, so there's a high social cost. At the same time, many people feel that there's a state obligation to ensure that people who are arrested ultimately show up at their trial, and also don't harm the public in the interim time period. So we have these two competing interests: individual interests, social interests, family interests, employment interests, and then also the state's interest in ensuring that people show up to trial and don't do public harm. I'm going to talk about a context where we only care about flight risk, just to keep things super simple, but everything I'm talking about extends to this broader context as well. Okay, so how is this decision normally made? Often it's made over video conference, a few minutes of discussion between the judge, the public defender, the defendant, the prosecutor. And you can imagine, and this is typically how it's done for decades, and you can imagine there are all sorts of problems with this. I mean, implicit bias can creep in, even explicit bias, inefficiency, just inconsistency, a lack of transparency. And so there's this move recently, actually not even that recently, but there's this move to using algorithmic tools to help guide these decisions. And in theory, these are quite simple. So now I'm going to put on my data science hat and throw caution to the wind. Forget about causal inference. We're going to treat this as a pure prediction problem, and then we're going to come back and see how we deal with that. And so as a pure prediction problem, it's very simple. I have lots of cases. Sometimes I have hundreds of thousands, millions of cases. Sometimes, so I've detailed history about the defendant, their characteristics, their criminal history, details of their case. I know that some, when they're released, they end up coming back, they show up, and others they don't. So I have all this information, so I'm just going to fit some complex black box ML model, your favorite thing. You can fit a random forest, regularized regression, whatever you want to do, just fit it. And this is implicitly assuming unconfoundedness. So it's assuming that we have access to all the information that we need to predict these counterfactuals. So what am I predicting? I'm saying, if I were to release this individual, what's the likelihood that they would show up at trial? So this is inherently a causal question. It's about this intervention. If I were to intervene and release this individual, what is ultimately going to happen? Okay, so it's a causal question. It's trying to give me a counterfactual estimate, but I'm just going to treat it as straight up black box prediction. Okay, and now I have this probability for every individual. So 10% chance of showing up, 30% chance of showing up, 5% chance of showing up. And now I'm going to set a threshold as a policymaker and say I will release everyone who has at least a 70% chance of showing up. Otherwise, I'm going to detain them. Okay. So it's very sort of simple. If I don't think too much about the causal inference, it's very simple, at least mechanically, to set this up. Okay, so now how do I evaluate these things? So first, notice that there's every threshold that I set. So first I have to get these predictions, but every threshold that I set corresponds to a different policy. And by policy, I just mean a decision rule that says release or detain for any individual. And so every threshold is a policy. And for every policy, I want to understand the relationship between two quantities. The first is the proportion that are released under that policy. And that's pretty straightforward. I can just apply that to historical data, and I say, okay, well, if I were to just go back, assuming that the distribution of characteristics doesn't change over time, I can just go back and say, if I were to apply this policy to this population, this number of people would be released. That's easy. Now, the second part is I want to know how many people would fail to appear if I were to apply that decision rule. And again, this is a causal question. Why is that? Because if the policy suggests demanding bail from someone who in reality was released in our data, or suggest releasing someone from whom bail was demanded, now I have this counterfactual estimation again. And so it's not entirely obvious how I can do this. But again, right now I'm going to throw caution to the wind and just say, we're going to treat this as a straight up black box prediction problem. I have lots of data, I have lots of features. I can just say, if I were to intervene in this way, what would happen? Again, this is a counterfactual prediction, but I can at least mechanically just treat it as a prediction problem. And underneath the hood, it's assuming this unconfoundedness. Okay, so let's just go with this for now. And we're going to return to this omitted variable bias in a minute. But let's just say that we can mechanically do this so we can see what happens. So here is, I'm going to show the results in a minute. So here on the x-axis is the proportion who are released, the proportion who are ROR'd, released on their own recognizance. On the y-axis is the proportion who fail to appear at trial. That dot right over there in the middle is the status quo. So this is data from a large urban jurisdiction. So about 70% of people in that jurisdiction are released, and about 13% of people overall, of defendants overall, fail to appear at trial. And so if I release more people, I'm going to get more people to fail to appear. And so there's this trade-off. And now I'm just going to plot the curve that I get from this exercise that I just described. So every point on this curve is a policy. The policy corresponds to a probability threshold of when I'm going to release somebody. So on the right-hand side, I'm going to release almost everyone. I'm going to say, okay, it doesn't matter really how risky you are. Even if there's a 90% chance that you're going to fail to appear, I'm going to release you. On the left-hand side, I'm going to be pretty cautious. I'm not going to release that many people. And here we see this relationship between my estimated, so the x-axis is more or less ground truth. The y-axis is estimated based on these counterfactual estimates that I had to create. And the point is that if we just look at that in fact, we can see that if we go to the right of that point and see where it intersects the dashed line, we can in fact release many, many more people without getting an added failure to appear rate. And so putting this in quantitative terms, about 50% fewer defendants can be detained without increasing the overall flight risk. So this is pretty substantial. And just to give you a point of reference, on any given day, there are about 400,000 people who are sitting in jail pre-trial. And so if we can reduce this by, this is a non-negligible percentage, this is significant human cost. And again, if we're quantifying our social cost, there's the state's obligation in terms of flight risk, we haven't given up anything on that dimension. Okay, so now so far, again, and this is all still contingent on believing these estimates, and I'm going to come back to it in a minute. I don't want you to think that I forgot about that, but here we're just going to go through this exercise of saying, let's just assume we have unconfoundedness, and then we'll come back. Now, one of the issues that comes up here is this is all black box algorithm, and this raises all sorts of concerns, particularly in the legal system. There's this issue of procedural due process, and so it's hard for a defendant to interrogate that algorithm to even understand what's going on. It's just lots of data come in, and then some decision comes out. Am I going to release or demand bail from this individual? And there's nothing else you can really do. So if we have perfect trust in the system, maybe that's fine. I think in practice, and for good reason, we don't. And so what are we going to do? We're going to create some very, very simple rules. So this is a statistically derived simple rule. It's just a heuristic. I won't tell you how we created it, but it is statistically derived. Basically, it's just a regression where we've scaled up and rounded the coefficients. And so how does this work? Well, you get points assigned for your age. So if you're younger, you have more points because you're riskier, as estimated by the algorithm. And if you have a previous history of failing to appear, then you also have higher points. So it's very simple. It's intuitive. We feel like this is mechanistic. We feel like we're getting something close to causal here, even though I'm not using the causal language here, but it's at least we're getting somewhere close to that. So how do we do this? Let's say I have a 35-year-old defendant With one missed court date, they'll get a score of 1 for their age, a score of 2 for their previous flight risk. So that's 3. Now we have to set a threshold. Let's say our threshold is 4. Then in that case, we'd say, okay, this person is relatively likely to show up to trial, and so we're going to release them. Okay, very simple. And we can even look at this graphically since it's only 2 dimensions. We can say everybody on the lower left here will be released because they're relatively low risk. Here I'm just setting a particular threshold. And so this is something that I could give to a judge. It's something I could give to a defendant, to a public defender, and say, this is the rule that we're going to use. It's not black box ML, but we can interrogate this particular rule. Another question is, how well does this work? And here the red dots are show the performance of this very simple rule for different thresholds. So the risk scores are calculated in the way of that table that I showed you earlier. But for every red dot here corresponds to a different release threshold. So am I going to release you if your score is 2? Am I going to release you if your score is 7? So wherever that is, it's going to give me different policies that I can implement. And the point here is, and this was quite surprising to me, is it's actually not that much of a loss in performance. And so we can still see that, so if it were perfect, all these red points would sit on that line. In fact, they're not that far off of it. And in fact, they're doing much better than the status quo. So I can still, if you look at the red point right to the right of the status quo black dot, we can see that we can still release substantially more defendants. And as estimated, at least by our model, we can have a lower overall flight risk than under the status quo. So here it's pointing to the fact of why, when black box prediction is problematic in some of these high stakes settings where we need to explain to individuals who are affected by the intervention why we came to that decision. In fact, there's not as severe a trade-off in many contexts as one might expect. So that's good news. And we repeated this exercise in a lot of different domains. And it does seem to be, it's not universal certainly, but it does seem to hold in many different domains, which was surprising. To us, although there is a long history going back decades that establishes the efficacy of these simple, improper linear models in making these types of risk assessments. Okay, so now I want to return back to this omitted variable question, which I've been slipping under the rug. And of course, there's this problem of confounding, that judges do have access to more information than is recorded in the data. So judges are interacting with the defendant, they have body language, they have conversational elements, they have attitude, so certainly have more information. And the worry is that we don't have some kind of ignorability here. It's not the case that those defendants, conditioning on all the available information we have, it's not the case that those defendants who are released are the exact same as those defendants from whom bail was demanded from. And so we can't necessarily just assume that we're in that world and carry out this prediction exercise the way that I did earlier. So that's the obvious problem. And so how do we deal with this? Well, there are lots of ways to deal with this. I mean, one is sensitivity analysis. And so this is a classical technique in causal inference that I'm sure many people in the room are quite familiar with. But it's actually, maybe somewhat surprisingly, has not really made its way into the machine learning community so much, even though I do think it's quite powerful. And so there are lots and lots of different ways of doing sensitivity analysis. So I'm just going to quickly review one of the original ways of doing this, which I think is still quite powerful, Rosenbaum and Rubin sensitivity analysis. So here you posit some model of confounding, and it's a very simple model. You assume that there's a binary covariate, and so this is encapsulating all of the information that judges have that are not recorded in the data. And the model assumes that this binary covariate, it affects both the judge's decision. The judge's decision is to release or require bail, and the eventual outcome that the defendant will appear at trial or fail to appear at trial. Okay? And in this framework, there are 4 parameters that you have to specify. So you have to specify the overall proportion of U in the population, the likelihood that U equals 1 versus the likelihood that U equals 0. So how is this extra information distributed in the population? The effect of U on the judge's decision. How much more likely are they to release somebody conditional on U being 0 versus 1? The effect of U on the defendant's likelihood of failing to appear if released. And then finally, the effect of U on the defendant's likelihood of failing to appear if bail is required. So it's quite natural in saying that you have to specify there are all these connections that we assume is what's driving the confounding, how that hidden covariate affects the judge's decision and how it affects the outcome. And it affects the outcome in these two different ways. That if action A is taken, it'll affect the outcome. If action B is taken, it'll affect the outcome. And we have to understand all these relationships. And so this model says, well, this is just something you have to posit. And so this is maybe where your domain expertise is coming in. Say, well, we have a sense of what that extra information is, and so we're going to posit the structure and scale of that. Okay, so when we do that, let's see what happens. So here's the original plot that I showed you earlier. Now if we allow for this unmeasured confounding to double the odds of a judge releasing an individual conditional on this U, and doubling the odds that an individual, that a defendant will flee if released, and also up to double the odds that a defendant will flee if bail is demanded. So all of these are pretty extreme. But if we do this, what do we get? We get this band, this sensitivity band. So I don't know if you can see this, it's a light gray band. Showing us how much our estimates might change if we actually were to pin these things down in those ranges. So if we were to allow this hidden confounding to vary up until this certain level of somewhere anywhere between 0 to 2, what is going to happen? And so it's a very simple model, but now we're talking about causal effects. We don't know exactly what it is, but we know that it's assuming this model of confounding holds and the scale of confounding is correct, then this gives us an estimate of what the true causal effect will be. And we can repeat this for any choice of parameters. So here's a larger set of parameters. So this is saying now we're going to let the causal, or now we're going to let the hidden confounding vary up to a factor of 3. We're going to get bigger bands, and quite naturally. But now again, this is getting us at that causal estimate. So we can't pin it down because there is unmeasured confounding. So we're not going to precisely be able to pin it down. But going with prediction and coupling it with assumptions about what the magnitude of that unmeasured confounding might be, we can get reasonably good bounds on what we can expect the outcome to be if we were to implement this type of policy. Okay, so now just wrapping up and returning to this initial question, is prediction enough? I'll say, well, it depends on what your definition of prediction is, and there are at least a few different points that are important to keep in mind. So first, in many contexts, including legal contexts, predictions must be explainable. So this is, again, our concept of procedural due process. Also, it's if we're trying to get into something more of a causal mechanism, we don't want these black box predictions, but we want to understand in some way what is driving the decision. Well, we can think of this as constrained prediction, although it's not the standard way of facing a prediction problem, but we can certainly do it. The second is that we often need to estimate counterfactuals, and this is the hallmark of causal inference. But again, we can just think of this as robust prediction. So if we, it's just, again, maybe this is an abuse of the word prediction, but I think this is where a lot of the machine learning machinery is coming in, is that we have these models, and if we really do believe implicitly that there's implicitly or explicitly that we have some kind of unconfoundedness, and if we have more and more data, maybe that assumption is more realistic, then estimating counterfactuals is analogous to a standard prediction. And then finally, predictions are not policy in the sense that, even in the causal inference sense, that if I just tell you what the counterfactual estimate is, if I were to take this action, I can, in best case, know what the world might look like, but that doesn't tell me anything about alternative actions that I could have taken. So going back to this pretrial example, let's just say that I know for sure that someone is high risk of fleeing if I were to release them. That doesn't necessarily mean that I should detain them. Maybe that means I should intervene by sending them a text message reminder, which many jurisdictions are doing. Maybe that means I should give them a transportation voucher, or maybe I should give them childcare benefit to make sure that they come to court. Or maybe it means that I should just end money bail altogether because it's actually more equitable from the social utility to do this. And this is not a problem that's pure prediction versus pure causal inference. We always have this. But if I want to kind of rephrase this in terms of prediction might be, or we can at least look at everything through the lens of prediction, I might say, well, what are the long-term effects, and that's a predictive question, of if we look at the entire family of policies that we could possibly implement. Now, this again is almost a tautological definition of prediction. We're saying if I could look at every possible set of family of policies, and now I can forecast 20 years from now, what are the effects of these things? Sure, that's a prediction question, but it's getting quite close to what we think of as causal inference. And I think this helps bridge this technical gap between machine learning and causal inference and how it plays out in practice. Thanks. I should say, if you want to read more about this, you can check out the papers that are posted on this.
Great, thanks so much. That was terrific. So next we have Mike Baiocchi, and like Sharad, he defies easy disciplinary categorization. His original phenotype was as a statistician. He still retains that, but he also works as sort of an interventional global health expert as well, working in the field and trying to make change there. So we like to call him an epidemiologist or clinical trialist too. So you can't label him with just one name. So Mike.
So I'm Mike, and my label is I'm a statistician. And that actually matters. That's actually something I'm very passionate about, and I chose that for a very specific reason. Being a statistician means that we are the defenders of the scientific method. We are the ones, through several generations, who took the scientific method and codified it, mathematized it, quantified it, and we are the ones who work with applied researchers. We go out past the walls of the gate and we find with them new knowledge and bring it back. We're the ones who help them demarcate between something that's useful and something that's fool's gold. This moment right now that we're sitting in this very moment, is really important. This is the moment that I have trained for. The academic barbarians are at the gate. And I'm one of the statisticians who is on the rampart. And we will hold this line because it matters. Because there are consequences if the ivory tower falls. That's where we put all of our information, where we have put our human knowledge. And the consequences really are meaningful. They are things like people will die. People will get hurt. And we don't want that. And we want to make sure that every piece of knowledge we bring in has been vetted and thought through carefully. And that is what's at stake. Right. Oh, that was so much fun to say. So what I'm going to do is I'm going to tell you where there is intersection. And I think the machine learning folks have correctly seen that there are places where we can team up. But I'm going to show that God bless their hearts, they have an incorrect understanding of where their roles should be. So when I think about data, I often think about a data table. So the first column there is a person ID, the second is a generic treatment, and we have a generic outcome. So we have in this table 10,000 people, we have a binary treatment, and we have some set of outcomes. This is usually the way that a data table shows up. And this is the way that most of us will store our data. This is not the correct way to think about data if you were going to go after a causal estimate. In fact, what you should do is think about these two implicit columns. These are the outcomes for people who have taken the control, and these are the outcomes for the people who have taken the treatment. And everybody has a potential outcome. Until we assign the treatment, we don't know which one we will be able to see, but those exist. And it would be really useful to be able to know both of those numbers, but we won't be able to. Because as soon as we assign someone to a treatment, and we'll get that number, we lose the ability to see their control. This is known as the fundamental problem of causality. If I assign someone to control, I'll get to see that number, but I will not get to see their treatment. Right? And this is problematic. Sometimes, and this is important, this is sometimes referred to as a science table. So if you want to look it up, check it out. It's really a clever way to think about causality. So we can go on, so on and so forth, based on the treatment assignment, and then we go through and we collect our information. We can actually put it, this is the same amount of information, we have just sort of done it in a really expressive way. You can now sort of see why, incorrectly, the machine learners think that this is now a prediction problem. This quantity right here is unknown, but maybe we can do a good job of predicting it. So let's pause just for a moment. This is causal inference as a prediction. Right here, one not unreasonable thing to do that feels not terribly wrong, because it's the way we probably trained you in the basic classes when you thought about experimental design, is if you want to figure out what's going on with the control, you would take the observed values and average them. So you got about roughly 29 here. and take the treatment and average it, and you get like a 78. So there's something like, 50-ish units. So the treatment looks 50 units better. Put that in the back of your head. We'll come back to that. So you can see, again, why machine learners think that this might be a useful framework for them to start engaging this problem. Because what they do really well is they take a bunch of x's and they give us good values of y. And if you spot me a moment for to use a linear model, this is obviously not the fancy versions that they can do. We can maybe parse this out and we can look at the variables, some particular thing like age, and maybe think about this value as being its connection to the outcome. That is tantalizingly close to something that would feel like a causal estimate. As I start seeing x change, maybe I should change my y by that beta amount. But that's not a causal estimate. In fact, one of the deep lies of regression, the way that we've shown this to you before, is to have this equality sign. It feels like, if you've done math before, that I can solve for different parts of the equation. And that's in no way true. We probably should have put like an arrow here. If you were to switch things around, you would get very different estimates, and they are not actually equal to each other. This is an important feature of prediction. I won't go too much more into this, except to say that, and I'm not going to steal any of his thunder, because he's got Wagnerian levels of thunder in this paper. But David Donahoe has, and I noticed it was referenced earlier, this great paper, 50 Years of Data Science, that sort of outlines, and one particular part that I want to bring up, outlines when does machine learning do really well. This is an oversimplification, but it's basically when you can get a bunch of chances to evaluate whether you're right or not. That is not causal inference. That is wildly not causal inference. That is a prediction setup. And so machine learning, some of the ways that it has been constantly winning don't replicate over here. So keep that in the back of your head. All right, so the problem that I'm setting up here right now, one might call confounding. But there's other kinds of problems with getting at the science table, thinking about what else could have been. What are these blank values? And I understand. Oh, wait, I'm going to back up. Let me do a little bit of a trick for you. So we have all these ones and zeros. I'm going to rip those out. I'm going to put in the exact opposite. So take what we had, take out the treatments. I'm going to flip it around. And I'm going to switch out the kind of data that we have. So everything that was visible before is gone. Everything that we didn't see before is now there. So I flipped the treatment and control. And now I'll do that same trick, which you might have learned in Stat 101, which is to take the averages of what you see and look at the difference. And now we've got 73 and 34, but in the exact opposite direction. Right? So we now got instead of a plus 50, we've now got a minus 40. That's crazy. Right? So this is a problem with confounding. If we had more x's, maybe we could do a better job of getting at what's going on here. This is confounding. I think the machine learners are onto that. They figured that out. But I'm going to blow your mind because there's a couple other problems. And they come from these guys over here. And they haven't really been explored in machine learning. These are really important. I would say even more important in the modern era. And though I keep telling my machine learner friends that these are important, they don't seem to want to engage. And I understand these are old concepts. They're musty. And they're basically, I get it, right? So what I propose, after looking into the machine learning literature, is to make this a little bit more palatable. And so what I'm going to do is I'm going to introduce here for the very first time the idea of Bartasius's demon. And the idea behind Bartasius's demon is whenever you do not have randomized data, you have not randomized people in treatment control, you've not done a simple random sample, Bartasius's demon is in charge. And so, I think that this sort of, oh, wait, let me hold on 1 minute. Yeah, okay. I think this matches the machine learner sort of way of naming, because I think it collapses a bunch of ideas into one. So it's not very specific. It's not evocative, so it doesn't tell you really what's going on. You can't figure out what the meaning is. But it's super interesting, and I want to look into it. So I think this matches how the machine learners like to name things. Correct me if I'm wrong. Oh, and the other thing is that it's an obscure reference. So Bartasius was my high school freshman year science teacher. And the story is that this was an experimental class. It's the first time I engaged. It was lab science, and I had to take chemicals and mix them up and explode and that kind of. I don't think I was supposed to explode, but they did explode. And I just got rubbish data all the time. And one of the things that Mr. Bartasius would love to do is he would look over in the middle of these scientific experiments and be like, hey, baiocchi, I think science hates you. So I'm naming this in honor of Mr. Bartasius because I think science hates us and always trying to mess with our data tables. All right? So let's pause and let's see if this is something that's useful for us. So are there real-world demons, Bartasius demons? So claiming something exists is not the same thing as naming in the world, right? So can you point to an example in the world? Just do it in your head. Give me a minute. I'm going to journal. All right. Did anybody get a doctor? Yeah? Okay, this is, so. So I do mean this actually seriously. I mean, he's a great guy, but yeah. So physicians try to select the best intervention. That is their job. They are wildly not randomizing, and if they did, oh my gosh, don't tell me that. They are choosing based on information that they have, and they are little detection machines. They are abstracting features from the world and trying to figure out what is the best intervention. So they are not randomizing for us. They are making our job as difficult as possible, right? Because they are trying to optimally put people. They're trying to sort them in a way that we're not aware of. In this part here, we're not good at recording their insights. We are not flawlessly getting everything in front of us in the data analysts so we can back into what's going on. So yes, Bartasius' demons do exist, and they're really, really important for our research. Okay, I'm going to tell you, using my own research, motivating from my research, two of the other problems. I think this is the causal inference problem that when you take a causal inference class, this is the kind of stuff we teach you about. We teach you about the two groups start off different, let's make them the same, then we can do good causal inference. I'm going to tell you about two other problems from my own particular research that will show why this is not all of the problem of causal inference. So the first one is, I have two lines of research. This one is sexual assault prevention. Based on ideas that were sort of codified in the early 2000s, like sort of feminist theory about power gradients and empowerment, we've developed a sexual assault prevention program. And we're deploying it in the slums of Nairobi, Kenya. We've been doing this for about 5 years. We teach in schools to middle school girls and middle school boys. And we have awesome trainers who we've recruited from the slums themselves, and they model really cool, good behaviors. They teach people how to interact. They teach them about better social norms, that kind of stuff. And we also teach them how to kick butt. We teach them like physical defense, Brazilian Jiu-Jitsu, Krav Maga. And so this has been a really awesome line of research. I spend usually about a month or two in country getting things ready, training folks up, our trainers, and also negotiating with schools, administrators, to get us into the classroom so we can teach. About 3 years ago, we finished a cluster randomized trial of this intervention. We're running a much larger version of this study now. We worked with 30 schools. We had 6,000 middle school girls. Middle school girls that we worked with. And long story short, we were able to take the rate of rape from 7% and cut that in half. And we know that because we randomized and we did careful measurements and we thought very carefully about all the different causal pathways. So let me get back to a data table. Here is a very simulated data set. I've got 6,000 people. I've got whether, girls, and I've got whether they were trained or not and whether they were assaulted or not. Where's the problem? Let me give you a hint. Is it?
Showed up for training. There's something different about them.
Just chill. This is totally like rhetorical. It's great guesses. Great guesses. Great guesses. So what's the problem? So does this help you? No? Oh, it's perfectly named then. So you can't see it. It's not there. It's literally not there. There are a bunch of observations that didn't show up in my study. These are the girls who are in the toughest situations. So we had a school that we were training in, and we slowly discovered that one of the administrators was assaulting some of the girls. So we lost that. So it is actively censored from our data set. right? I can't do prediction on those kinds of people who have probably a higher probability of being assaulted. I've lost, in some censored way, information that's really important for predicting a counterfactual. And this is really hard because I can't say anything about data I don't know, right? If I'm going to tread into kinds of parts of the world that I don't have data, I'm going to be doing that with assumptions. And that isn't really science. That's guesswork. The second problem, which is closely related, is this is hard to detect. These people, this person 7078, literally doesn't show up in my data set. So it's hard to tell that I'm missing that without content expert knowledge about why the data didn't show up and that the data should have been there. This is important. This will mess you up. If you want to sort of follow up on these kinds of ideas, there's an active area of research called transportability. One of my favorite researchers, Liz Stewart, is on this. She's great if you want to read about this kind of stuff. We, the causal inference folks, have started to think about and talk about this as inclusion-exclusion criteria. We have come up with methods for helping to communicate the barriers or the where do not tread happens. So we have like table ones or balance tables that tell you about who we studied, and you can get a sense of who we didn't study. Same thing with the inclusion-exclusion. Second example is work I do in cardiothoracic surgery. So cardiothoracic surgery is interesting. So in this case, turns out that your heart can break, literally, and they can go in and fix it with things. And you want to know if that thing's the right thing or you want to use the other thing, okay? I work with some wonderful surgeons, and that's their part. So Dr. Wu, Dr. Chu, and Dr. Goldstone. So cardiothoracic surgery is hard to do randomized trials for a couple different practical reasons. One is getting consent is hard. Like one of our studies is about aortic dissection. So literally, like you've blown, like your blood is dripping out. And it's awful and it's terrifying. And you can't get consent in that case. The person is not going to be able to sign into this because they didn't have the condition a moment ago and they are currently rupturing, right? So getting people into your study can be really hard. But it's a really important question. How should we treat these people? The other thing is, for this particular example, was the speed of innovation is crazy. So in order to get enough people to have the power to detect a causal difference, you'd have to sort of get 10, 15 years of data. But every like 2 years, maybe even 6 months, they come out with a new valve that you can replace. So the pace at which we are advancing, it's hard to use a prospective randomized trial to get the kind of information you want. But we still very much want to know that there's evidence of benefit. So we need to deploy these kinds of observational studies. So where can we get data like this? Well, maybe we can sort of use billing codes. They weren't designed for science, but they are sort of passively recorded. We can abstract these records, and maybe they will be useful. And I'll pause here. So big data is an awful label. It is totally about branding. It was meant to sell servers and get like NIH funding and NSF funding. If we had been honest in naming big data, we would have called it cheap data. Its key feature is that it's cheap to get, it's cheap to store, and then the subsequent downstream thing is that it gets big in that environment. But the cheap is also important to understand because these are bad measurements. They are not measuring the things that we want, and they are problematic in a way that a gold standard would not be. And we are not acknowledging that. When we use ICD-9 codes, we are using kind of junk, right? And we need to acknowledge that. So let me play this out for you. So again, we've got the person ID, and yay, big data, 3,000 people, or 300,000 people. We have ejection fraction, so that is like lub-dub. It's the amount of volume that you're sort of putting through your heart on each pump. Sort of like mid-60s is good, 20s is like, alive is like, eh, and then dead is like, eh. So those are the variables. Where's the problem here? And again, this is rhetorical. Where's the problem here? This one's a little bit hard to detect, but let me give you a hint using some of our newly developed nomenclature. Is that helpful? It's right here. I feel like this was a giveaway, right? 666, 666. Those are measured with measurement error. Those are not the correct measurements. That is super hard to tell. Measurement error in my world is almost never random. When we typically teach it to you, because it's mathematically easy, we will think about measurement error as just sprinkling some noise on top of the number that you're interested in. That is not happening, especially in medicine. Why? Won't go into this too much, but there's sort of incentives, like especially with billing codes. Maybe if there's one that's a little bit of a cheaper procedure and the one's a little bit more expensive, it might go in one way more than it goes in the other. Right? So these are important measurements, and they're systematic measurement errors. I forgot to mention this, but Miguel, a couple of years ago, and actually even yesterday, given a really good talk that talked about the first part, where the inclusion-exclusion, I think, is a real problem that we haven't been addressing. I would also say that this is another problem that we have not been addressing, is thinking about the passively collected big data and how to fix the measurement error problem. So to draw this connection back to ML, so with machine learning, this isn't a huge problem, because what we're interested in is really contained in the variable that one variable. So we're only interested in, I don't care how, whatever corrupted number you're using to get your prediction, as long as that corruption sort of stays the same in the future. So you can sort of like condition out the things that you don't need, and the measurement error problem sort of goes away. But we can't nuisance out the treatment intervention. Now we've got two variables that are part of our core statistic, because we want to know, how does the outcome relate to the treatment? So we're now bringing more things into the core of what we're trying to understand. So that's a problem. That's not usual or for the machine learners. So I would argue that measurement error is probably one of the most insidious problems, because you see a number in your data table and it feels like the real number. And if you don't have intuitions, if you don't understand where that number came from, you will trust it and you will be wrong and you will have a biased answer, almost surely. Right? I refer to measurement error as the carbon monoxide poisoning of data analysis, because it will make you hallucinate and it might kill you. Right? Okay, drawing it all together. The fundamentals have not changed. The fundamentals of causal inference are still the same. Machine learning is a bunch of new tools, but they're just tools. Machine learners are just tools.
You want to rephrase it.
We know the main issues. Causal inference has been working for a very long time on this, and we have put these out as like recommendations. You can read along. It's almost like a Mad Libs. If you look at the consort guidelines or like the strobe guidelines, we have worked out the places that causal inference can go wrong, and we tell you where to report and how to report those. Just read. Sorry. And if you want to read, you can also go back. There are philosophers who've been working on this forever. The empiricists, David Hume, John Stuart Mill, Fisher, Karl Popper. You can get some really in-depth ideas here. But here's my one conciliatory point is, so when technology increases, we can accomplish new things. We can move faster, we can get bigger ideas, we can do more things. And it is really important to recognize that there's going to be a shift in the composition of errors. So one of the points that Miguel made yesterday is, and I've heard him coupled with another point he's made in the past, is it used to be really hard to get a bunch of covariates. That's not so hard anymore. We can now use big data to get a ton of covariates. So maybe it's not, the confounding thing is not so much of a problem. The other, but maybe now we have to worry about measurement error, those kinds of things. So the feature of our new environment, as our tools change, we have to think about like how frequently we should pay attention to certain kinds of problems, but the problems are still the same. Okay, so that's the only concession I'm going to give. Do I have a little bit more time, or is that?
It would be, it depends on, it would be best if we could
Okay.
wrap it up quickly.
So
You can say more in the discussion.
yeah, I think I'll stop there.
Okay. So we have to discuss this Cristobal Young, sociologist, and Miguel, and our third is yes, and Ramesh, yes, from MIT. Wrong car, right? Yes. Our femto photographer. Yeah, so if everybody could come up. So Cristobal, Miguel. So who wants to start?
Should we get the speakers?
Yes, we should get the, they can come up. Whoever wants to start can start. And then we'll be joined by the speakers.
now you just go there?
Why don't you just use that? You can set up. Stand up here if you want.
Yeah, okay. It just seems a bit more straightforward. Okay, so really interesting presentations. Machine learning is really on the rise. I'm a social scientist, I'm a sociologist, a quantitative researcher, teach graduate statistics, think a lot about this stuff, observe a lot of conversations between the sort of rising machine learning work and classical sort of social science analysis. And there's a lot of enthusiasm about machine learning and what we can learn from these models, and there's a great deal of confusion. One stumbling block that I'll emphasize today is that standard machine learning is really focused on predictive modeling, and that's very different than a treatment effects analysis. And I just want to sort of point out two basic ways that seems to be causing a lot of confusion in my discipline. So in social science, basically everything we're doing is about a treatment effects analysis. We have one variable of interest. We want to know how it affects some outcome. Prediction is just about the outcome. Anything that predicts the outcome goes into the model, and that's what we're interested in. Treatment effects is really all about the XY relationship. So this is setting up a problem because predictive models don't tell you specifically about the XY relationship very well. And predictive models and treatment effects models will include different kinds of variables in their analysis, and they will give you different answers to your question. So one is problem of missing control variables in a predictive model. Treatment effects analysis is not really focused on prediction, but it's really focused on the idea of conditioning. Okay, we're trying to do regression adjustment. We're not trying to predict an outcome per se. We're not thinking about predictor variables. We're thinking about control variables. And these have different criteria. Specifically, a predictor is just correlated with Y. A control has to be correlated with both Y and X, both with the treatment and with the outcome. So I just want to emphasize that predictive models often exclude variables that would be really important in a treatment effects analysis. And specifically, that would be a variable, what I would call a control variable that has a weak correlation with the outcome, so it's not a very good predictor, but it has a really strong correlation with the treatment. And these kinds of variables don't contribute to the quality of the prediction, but they change the treatment effects analysis quite a bit. They have a big effect on the parameter estimates. So these kinds of variables, we'll call them X variables, that are very important, are often, so predictive models are often missing a key set of variables that are really important for treatment effects. And when machine learning and classical social scientists come and talk to each other, they just don't recognize that they're using two different criteria for how you include variables in your model. So this is just one of them, and it basically comes down to remember that there's an omitted variables bias formula, and the reason why we include controls is not to predict the outcome. It's to address the XY relationship. They predict the outcome and they predict the treatment. And predictive models just sort of miss one half of this definition. So that's just a basic reason why predictive models give different answers. And the second example I want to give you is what I would call bad controls. So there are a lot of important cases where a variable would have an enormous predictive impact and would seem to obviously belong in a predictive model, but really biases our treatment effects analysis, our causal analysis, and should not be included in the model. So sometimes really good predictors are really bad control variables. I'll give an example. Last year, Google published a data analysis of gender discrimination within their company. So, is Google the kind of company where both men and women can thrive and succeed and contribute a lot, and empirically analyzes what are the wages of men and women, and are they fundamentally different, systematically different? So Google pointed out that, well, if you just look at the data, yes, women are paid much less than men. But if you control for promotions, then the pay is the same. And they were very satisfied, and they concluded that there's gender parity within the company. So promotion is a really strong predictor of wages, but it's also the central pathway through which gender discrimination can occur within the company. And so including it as a control variable in a treatment effects analysis where we're trying to understand the effect of gender on wages is a really bad step, because it's basically saying the company might as well have issued the report and also said, yes, we pay women less, but that's just because we didn't promote them. Okay, so they're sort of explaining away the pathway through which discrimination happens. So, the conclusions we get from this are wrong because they thought about it as a predictive problem, and promotion obviously is a very big predictor of wages, but it's really bad as a control variable. It's very problematic as a control variable. And by including this predictor, essentially we invoke a lot of assumptions about how the company works. We assume that Google nurtures female talent, recognizes female contributions, and ultimately promotes women in a truly egalitarian and meritocratic way. And in my view, that's the same as just assuming that there's no discrimination within the company. And we can't test any of these assumptions. So this is a classic. Sometimes it's called a post-treatment control. Sometimes it's called controlling on intermediate outcomes. But it's a classic case. You have this variable. It's a very strong predictor, but it's very problematic as a control variable. So sometimes the strongest predictors should be excluded from a treatment effects analysis. So I bring these up in just two ways in which a predictive modeling exercise can lead to a very different analysis than a treatment effects framework. And I don't raise this as a critique of Sharad or of Mike's analyses in any way. I think we're all sort of aware of these, but these are points of confusion that I've seen in my discipline that I think we need to be more aware of and talk more about and recognize the differences between a predictive and a treatment effects analysis, and see how we can do a better job of bringing machine learning more in line with the kinds of questions and the kinds of analytic questions that we're asking in social science. That's where I'll leave off. Thanks.
Thank you. So I just want to point out one of the important outputs of this meeting is not just the engagement on the central conceptual issues, but understanding the language that the different disciplines are using to talk about the same things. And if we don't get on the same table with understanding what people are calling these different things, we have these, we're ships passing in the night. So I think it's very, very useful to hear these presentations from different disciplines, hearing how they formulate this sort of classic problems that, as Mike has pointed out, and Miguel have existed sort of from time immemorial. So, Ramesh.
Sure. Thank you, Steve.
Okay.
Yeah. I'm Ramesh, and you need to turn it on.
Oh yeah, not quite on.
Hello.
There you go.
Yes, so I guess we're East Coasters. We'll represent the East Coast view a little bit. We thought we were going to come here and hear the ABCs of prediction, but I think very quickly we have moved to the AI, BI, CI of prediction. Artificial intelligence, biological intelligence as medical experts have it, and of course the CI, right? The causal inference. So it's fascinating to see this conversation. So Mike, you left kind of it open about our machine learning a daemon, which is mysterious. Where's Mike? Oh, you're back there. Are demons or are they tools? So would love to hear your thoughts when you come back here. And Sharad, I think your point on simplicity includes explainability. I think it's very well taken. So let me talk a little bit about how I see machine learning, and there are effectively kind of three major ways to think about where machine learning is and where it's going. And I also want to kind of make sure that we are talking about machine learning as not as it exists today, but where it could be 3 years or 5 years from now. Because remember, the most significant paper about AlexNet just came out about 5 years ago. So everything has happened in the last 5 years, all the major developments. So think about them as basically sensory, physical, and cognitive, 3 types of MLs. And by sensory, let's just call it digital. That's the way we think about it. Supervised, unsupervised learning, you have a lot of data, you want to make some inferences out of it. Then you have physical, where you actually interact with it, whether it's a robot or you click on something, you give drugs, and so on. And most of that is being solved with reinforcement learning. And the third, which is cognitive, where you really start thinking like human intelligence, where you have language and you have culture and many of the things that we're talking about. And for that, the algorithms are still emerging, right? So when we start thinking about these 3 buckets, a lot of the discussion we have about missing data or censoring and so on actually become very different mechanisms. One of the earliest work my group did at MIT is on something called automated machine learning, which in simple words means AIs writing AIs. And so the very first paper we wrote about 2-3 years ago showed that actually a lot of the things we talk about, like Nigam talks about data janitors or data wrangling, as it's called in machine learning, or how do we create the most optimal models, or are we even creating the right architectures, are actually just these really mundane problems for which machine learning engineers get paid for a lot of money, but they can also be automated. So if you're really worried about job losses, actually the machine learning engineers might be the first ones at risk. So what does that mean? So a lot of times when we're talking about statistical methods, we're talking about the features. And the same thing happened in computer vision or NLP, natural language processing, or machine learning in general, where in the beginning people really worried about doing feature engineering. How can we manually craft features so that we know we're looking at the right things? And what we quickly realized through convolutional neural nets is actually feature engineering, which we think is the human creativity, is actually meaningless. And actually the first couple of layers of neural nets that do feature engineering really well, because they just brute force search through all the possible features. And that search actually allows us to create the best features. So that battle has been won squarely by machine learning tools. Now it comes to the architecture itself, like what kind of machine learning algorithms or models and networks should you choose? And so as I said, 5 years ago, when AlexNet came around, which was just an 8-layer model, people thought, this is awesome. Somebody from Toronto has this amazing creativity to come up with this network that nobody had thought about. And later on, a few other models came around, like ResNet and VGGNets and so on. And what we showed about 3 years ago is that actually you can search for the most optimal machine learning model, something we call a teacher-student network. So there's a teacher that's very smart and is actually training lots of students. And not all students will become the best models, best networks, but some of them actually become pretty good. And we showed that with that method, this teacher-student method, we can beat all of the existing networks. Just think about that. We can beat all of them that involved significant human creativity just 3 or 4 years before that. So I've gone from feature engineering to automatic featuring, feature search, and right now we're going from kind of handcrafted machine learning algorithms to automatic search of machine learning algorithms. The good side of this, by the way, is that we thought, oh, maybe there's so few models that will actually be amazing. And most of the ones this teacher network is teaching, the student networks will not be very useful. But it's because there are only so many AlexNets, and there are so few networks that seem to be doing well. But actually, the analogy with schools is pretty good. Actually, the good news is that teachers can teach students, and actually most of the students end up doing reasonably well. And the news here is that actually you can, in fact, train most of these networks from scratch, and they end up doing pretty well, much better than what we can craft manually with human creativity. Okay, so I want to kind of bring that back into focus, because where the puck is going as opposed to where the puck is a very different world. And many of the things we talk about issues in missing, censoring, unlabeled, noisiness, all those things could potentially be taken care of in ways we don't even realize. And in the previous discussion, I talked about kind of the unreasonable power of data, and there are a bunch of papers in this space. If you just search for unreasonable data X, there are many papers in that category. And what it's showing is that we as humans we think linearly, but technology moves exponentially. So the way we are extrapolating of how these algorithms will solve our problems is unrealistic, because what happens is when you have humongous amount of data, it's not just that the algorithms that we're using today become slightly better, but a completely new set of algorithms emerge that were not useful with small amounts of data. And they solve problems in interesting ways. I was just talking to Nigam during the break, and one of the classic problems 3 years ago people were trying to solve is, if I give you a video clip, can you actually write the captions for it? And most of us in the field thought this is never going to happen. This is too challenging. We can barely recognize objects. But now, the caption can be that, hey, there's a man in this frame, and there's a cat that's lunging at the man is holding a coffee cup, and the coffee spilled on the shirt. Of course, the algorithm doesn't understand the humor in it, but nevertheless, it can get to the captions. And when it comes to the health data, medical data, I think we're in a similar space of interpreting and creating its inference, whether it's causal or not, based on what's going on out there, and be very aware of all the challenges that we have been talking about. One last thought is, a lot of this boils down to the UX and user interface. And that's the question I was asking last time, that instead of just entering fields, we had to get to a regime where we are interacting with the systems as if we are interacting with a child or a dog. And so when I'm teaching my 3-year-old, I'm not just giving her keywords, but I'm interacting with her in a real way. And we need to create similar UX if you have to start building reinforcement learning models for health, for EMR, and eventually for causal inferences.
Okay, thank you. So I'm glad that you mentioned that we are bringing wisdom from the East Coast. That means I don't have to apologize for my Boston accent anymore. People have heard enough of me today, so I'm going to keep this brief. I think that Mike put it very well, that the fundamental issues are the same, and we have better tools now. And the question is how we can use those tools. And I share your optimisms about a future in which these tools will be able to help us do things that we cannot do now. But probably not the optimism about the time scale. And it's not going to happen in the next week or the next year. And it's going to involve some method that we still don't know how to use, in which we are going to be able to teach our tools how to integrate expert knowledge. We are doing that, and in a very primitive way for some things that we are doing now. I mean, if you are talking about closed captioning, that's a relatively simple problem. If you compare that with the complex issues that go about how to prescribe a dose of a particular treatment for people with renal disease, etc., that's a much more complex problem. There may be a time, I hope, in which computers can learn that expert knowledge and can use it, because that's the key thing. For causal inference, we need to fill in the gaps of the data. And data are not enough. We'll fill in the gaps with expert knowledge, which makes all our inferences fallible. We may be wrong if our expert knowledge is wrong. That will never happen with other uses of data. So any use of data that only uses data could be better or worse. We can classify with 20% accuracy or with 70% accuracy, but we know how good we are. And there's nothing wrong about that. We can quantify how wrong we are. For causal inference, we cannot even quantify whether we are wrong or not, because we don't have a gold standard. We don't know. There is nothing in the data that tell us that tell us whether we are getting it right or not. Not even for average causal effects. So I believe in the future of machine learning, it will involve some form of combination of data with expert knowledge.
Thanks. So why don't Mike and Sharad, why don't you join us up here and see if there are some final discussion points from the audience. Okay, Nigam. We have our track star, Brianna. Megan, we should have just given you a permanent chair up here.
Then I can't make, I can't ask hard questions. Right?
Yeah.
So if the main problem is to figure out how often we're wrong, why can't we just empirically estimate that? We can create a library of 10 inferences or 100 inferences that we know are true or believe to be true, maybe 1,000 that we believe to be false. We test them on whatever data set we're going to use for asking the question we're really interested in, and just count how often do we get it wrong.
That's sort of what Odyssey is doing in the pharmacoepi realm.
Yeah, so that's what many people are doing and have been doing for decades. There are two problems with that. One is that, let me just focus on one problem. For most questions, we have no way of testing it because we don't know what the right answer is. If you ask me, should I eat 3 servings of fish per week? I don't know. I can tell you, based on a combination of data and subject matter knowledge, that, yeah, it seems like eating 3 servings of fish per week is better than eating 0 servings of fish per week. But how do I test it? There are no randomized experiments in humans who have been assigned to eating 3 servings of fish per week versus 0 servings of fish per week over a 20-year period. And even if we do that trial, people are not going to adhere to it. So we only have observational data to make these causal inferences. And for many, if not most inferences, there's no way of checking. Now, for a small subset, we can check. And that is what people have been doing. And that's great, because we learn something about what can be done and what cannot be done, which methods are better in each case. Sometimes Mike has written a lot about instrumental variables. Sometimes those methods would be better than using a propensity score, say. But it's very case specific. It's very difficult to make a general statement, a blanket statement about all new questions that are coming.
I think that's right. Well, I'm not sure. It's all contingent.
So who was right?
I think everybody's right, and I'm just going to bow out now. I think what we're interested in is unobservable, which is what would have happened for a particular person. And I think in the prediction case, what you would need in order to deploy a lot of the prediction techniques is to consistently randomize people into the different settings, and then you would get something that's quite useful. And I could imagine that might be a better way to, in the future, run randomized trials, is to sort of build a prediction model for any individual who's sort of running through that in some sort of like well-measured way for all the things that are happening for the person. But that's a reimagining of a randomized trial, and the fundamental part of the randomized trial is the key that we were actually in charge of the randomization, and so we sort of collapsed back into that.
Okay, sure.
So my background
So
is
just
more,
say who you are and Larico.
Hi, I'm Karen Sachs. My background is more in causal modeling and machine learning. So I was trained in a school that didn't have a stats department. Who's from that same school? There isn't one. There isn't one. Exactly. So I don't. So the word statistics is foreign to me. I did take a class. I don't know where that guy came from. Math department. Anyway. So maybe this question is naive because I don't know what statistics are, but but it seems to me like if you're building a predictive model, why not toss in causality? A causal model is a predictive model, and you sort of get something for nothing. You get this extra structure, and you get this extra insight into your domain. And the example you gave from Google, and I wasn't sure if you were arguing in favor of causal models or against causal models. In favor. Okay, that was a perfect example in favor. Why not? You sort of although it would seem to me that if I was calling it statistics, I could just do smarter statistics, and I would still see that, this variable is the mechanism by which. But anyway, but the general question is, why not just put a causal bent on it and get a predictive model with this extra beautiful feature that it's giving you insight into the structure of your domain and how things are happening.
If you look up hindsight learning, which is a pretty hot area.
Mike.
If you look up hindsight learning, which is effectively running experiments in the reverse direction, it's a form of what you're talking about in reinforcement learning.
But more generally, the people who are arguing for predictive models, I love predictive models. They're beautiful things. But why not put on the causal modeling bent when you're making a predictive model and get something for free?
So it's not for free. I completely agree with you. And for the kinds of questions that I'm concerned about, it's only going to be causal modeling, and I don't really want to even know the answers that come from predictive modeling because I'm not asking that question. So the issue is that causal models will give worse predictions. They'll do a poorer job of predicting the outcome in general because they will exclude things like intermediate outcomes. As I was saying, promotions will do a tremendous job at predicting wages. You're trying to predict wages, for example. Promotions will do a wonderful job of predicting wages. Definitely everyone who gets promoted gets a big wage increase. So that's an important predictor variable, but it's a bad control variable if you're trying to understand the causal effect of gender. Because
but gender affects promotion, and promotion affects salary. So it's a perfect predictive model, and it gives you good it's a perfect causal model with good predictions. Am I missing something?
Yes. So what happens if you include promotions in the causal model, in the treatment effects model, in any model, the effect of gender goes to zero, and there's no effect of gender once you control for promotions. Okay, and then one might conclude from that, oh, there's gender parity in the company. And that's the incorrect conclusion.
But your Bayesian network looks like this. Gender goes to promotion, promotion goes to salary. So you conclude that gender is actually the root variable here. I guess we can discuss it later.
Yeah, we're getting into some of the mechanics here. But overall, just if you look straight, and I've gotten into arguments with people, it's what variables should go into in a model when we're trying to predict an outcome, and what variables should go into it when we're trying to get a good causal estimate. And the variables that go into the causal model do a worse job at predicting the outcome. And so that's why.
That's your general answer, yeah.
This is why there's a confusion between treatment effects and predictive modeling. And you have a huge architecture now that does a great job at predicting, but isn't considering the criteria of causation.
There were also more, both Mike and Melgal can speak to this, but they didn't go into the details. But there are much more complex ways of framing the analysis than just certainly than just turning a switch and cutting one variable out and having a prediction model turn into a causal model. And I will let one of them speak to it more eloquently than I.
So there's a lot here, but I've never talked with God, right? So I don't know the actual DAG. I don't know the Bayesian structure that you refer to. I can create that when I do a randomized trial. I can flip a coin and put people in the treatment and control. So then I know that this has this has that sort of effect. So there's kind of a couple different things going on. Is like, what level of certainty do you have for the underlying data generating function? Right. So if you can write out, this always confused me about directed acyclic graphs, those causal models. You can write out all that web of complex interaction, but then you tell me that I'm not sure about this one arrow right here. Yeah, so there's all these other, I'm just saying, there's all these other things that you do know, all surrounding it, and that one arrow is the unknown piece, and that's the one that we're really interested in. That confuses me. How do I have that level of knowledge? Right, so I can tell you about the interlocking nature of all the variables that might be happening, except for the one that I'm really interested in. I don't know. It always struck me as a particularly weird thing to do, and that's why I think randomized trials have been so powerful. Is we intervene and we create a data generating function ourselves. I flip the coin. The machinery that we have set up in causal inference and experimental design now helps me establish a causal inference. So if I am passively receiving a data set, the ability to figure out what that number would be, connecting my treatment and my control, or the thing that I think is my treatment and my control, is predicated on a bunch of other interactions that I'm not directly in control of or aware of to enough of a level of degree of certainty that I can do more complicated things that you're talking about. I think so. let me back off a little bit and be like, yeah, I like your proposition, which is to think causally while doing, prediction. That will, I think, give you better insights into how we should move forward. I just don't know if the marriage is going to work in all possible ways, all possible scenarios.
And the models will look very profoundly different on different data sets. It's not as simple as taking the prediction model and surgically removing one or two because they're in the causal pathway.
It's not as simple, but if you actually care about intervening in a system, if your predictive model does not capture the underlying regulatory or causal structure, you're not going to do great predictions. Great perturbations. You're not going to do great interventions. That's why, anyway.
Right. Anyway.
You do great predictions, but bad intervention.
Yes.
Yeah, and maybe I come from molecular biology. In my domain, we care a lot about interventions. We see the cancer system, we want to fix it, and predicting is not the same as understanding.
Right. Oh, absolutely. Other comments from those assembled? Any last comments from the panelists?
If I can make one more pitch on the UX aspect of it, and I have worked with EMRs and I have worked with other health systems. And I think, and this is a question I brought up in the previous panel as well, I think maybe this forum is a good opportunity to maybe have one more conversation around what it means to interact with data. And all the insights and intelligence that experts are throwing away when they're not interacting with a specific kind of data entry-driven system is a lost opportunity. And I think Nigam showed a picture of some of the graphs, and I would love to use his system. But I think if we can capture that expertise, then in fact, things like hindsight learning will be amazing. Because instead of just saying this is what happened and this is what happened, if we can allow the experts to express the confidence, the possible causation, and all those variables. And then coming back to Mike's point, if we can create heat maps. So again, in hindsight learning, you have a notion of activation of particular neurons in the neural network. It says that how active was this piece of the algorithm when you used all this data. So that would tell you how much confidence you should have if you removed it or if you made modification to it. If you can create that explainable AI, then the UX for it will kind of go back and forth. So I think right now these two things are happening in silo, the expertise and the people who are building the algorithms, but hopefully can bring them together with a really good user interface.
Thank you for the great closing comment. So I think I'll just finish with an answer to the question, is prediction enough? And I think the answer is no. However, I will predict that we are able to meet in a year from now discussing these same topics, and we will probably rediscuss some of the things we've talked about today, but we'll also be able to engage with new evolution in the techniques as envisioned by Ramesh and Nigam and many of the others on the panel, and we'll see how far we've come. But anyway, let's thank our panelists and also thank you for your engagement.